Okay. Yeah. So in general, I thought I would put up a slide on the interests of the group, self-organization and complexity that I have at the Institute of Theoretical Physics. So I would say that it's actually dynamics of interface-dominated soft matter systems. What is our general interest and the modeling there? And I would distinguish this in on the one hand, relaxational structuring and pattern formation. So these are all systems that you start in some initial situation, and then they go back to some equilibrium state, right? And so examples are dewetting thin films or decomposing mixtures, evaporating thin films, and so on. And I will talk about the wet parts, so I will talk about drops on adaptive substrates. But it also includes colloidal crystallization on, or more generically, let's say, the relation between bifurcations and phase transitions. And then our strategy is then to take these relaxational models and introduce activity of different types, non-equilibrium elements in a controlled manner. So examples would be driven liquid films or drops on an incline, so forced contact lines, and deposition patterns at receding contact lines would be a very interesting field like coating technologies or laminar blotched transfer. But we also looked into spreading and instabilities of biofilms. And what I will talk about today is droplets of active liquids on the substrate. And this will be part of, let's say, our wider interest in bifurcations in generic active media models, right? So not very close to particular experiments, more, let's say, to ask what are generic models of certain types and how do they behave. And the methods we use, we range across a number of scales. Let's say it's all theory. So you mentioned experiments, but I'm sort of collaborating with experimentalists, but we have no experiment ourselves. And so my core field is like mesoscale hydrodynamics, phase field crystal models, phase field models, dynamic density functional theory, and if I need MD simulations, kinetic model, okay, we did this also ourselves. But if I need MD simulations or the macroscopic modeling, I go normally to find collaborations who really know how to do that. And so what I want today to talk about today is I will give you an introduction to gradient dynamics. Then I will use the drop on a polymer brush as an example. And then we move from, let's say, these passive models to the active case where we have to break the gradient dynamic structure. And as an example, we look at a relatively simple, but not that simple model for drops of active liquids on solid substrates. Okay, let's first talk about the passive case. And I introduce you to the idea of gradient dynamics in, let's say, or what I call gradient dynamics, right? I mean, many people do this in slightly different points of view. So, and let's assume you have a system you can describe by a scalar order parameter field, like a density or a film height or so on. And you wonder, okay, I know the statistical physics of that system. I know the underlying energy. What is the simplest dynamical model I can write down, right? And then you want to make a model close to thermodynamic equilibrium, so close to the minimum of the energy. And you say, okay, the simplest thing is I set up a dynamics for my field phi. So time derivative of phi is equal to some mobility times the variation of my energy function. That's like a gradient in functional space. And so this will guide me to the minimum. And this mobility has to be positive definite. Okay, but then someone comes, says, no, my system you cannot describe by this because my system has a conserved order parameter, right? So it's actually really a density that then cannot go out of the system. It's really just like diffusion. The mass is conserved in the system, and then this does not conserve mass, right? So I would call this a Elinkan type dynamics. And then you say, okay, my equation must have the shape of a conservation law, so it must be time derivative of the concentration or some other scalar field equal to the divergence of the flux. And then you write the flux as a mobility times the gradient of your variation, right? And this would be the Carnelian type model. And there are many models that that you can write like this. Okay, but then someone else comes and says, my system is much more complicated. I have many coupled scalar fields. I have n concentrations that live in a film of a certain height. So how do I expand this, generalize this to many fields? Okay, and then I say, you take the time change of your field with index alpha. It goes from 1 to n. And then each time evolution can actually now have contributions from, let's say, all the thermodynamic forces. And the thermodynamic forces are, let's say, the variations with all the different fields. And so you have this general structure of a conserved part of the dynamics. So this would be like convective motion in a liquid film. And then you can also have non-conserved parts. This would be, for instance, evaporation or the transition from a solute from the bulk of the film to the surface of the film, where it acts as effect. And then the only rule is that these Qs, these are now matrices, and they have to be positive definite to ensure positive entropy production, and they have to be symmetric, right? Okay, and this, if you say, okay, this, I do not want them to come out of blue sky, these equations, where do I get those from? Then I would say, then we go, for instance, to Onsager variation in principle that, for instance, Marcel Doy has promoted quite a lot the last years, and then you can get these equations. Okay, simple example is the diffusion equation. Actually, now I have a conserved concentration phi, right? Let's say in a bulk liquid, something diffuses a solute, and then it must have this form. And then from statistical physics, we know if it's dilute, the free energy is just entropy, right? Nothing else. And if you take now this free energy, take a mobility like this that you also can get from microscopic considerations, and you plug it in, you get phi times the gradient of the chemical potential is equal to the flux. And you calculate this gradient, and then you come just to the diffusion equation. And for free, you get the relation between the diffusion coefficient and the temperature. Right? So that would be, I think, the simplest example. And I always wonder why we do not teach this in the basic physics course for bachelor in the first year, essentially. So actually, I started to do this. Now, let's look at thin liquid films, because we want to talk about thin film models. So there, I say now I have an evaporating and dewetting thin film or a shallow droplet of simple liquid on a solid substrate. And if it can evaporate, I know it must have a non-conserved part, and then it can have convective motion inside the film. So I have a conserved part. So it must have this form. It's a scalar field. Now the energies. Some people call it an interface Hamiltonian. It is actually a ground potential. So what you have a droplet with a free surface with interface tension or energy gamma. And then this is a metric factor, the length of the interface, taking in long wave expansion, right? So normally it would be square root of 1 plus gradient of the height squared, and you expand this in Taylor expansion, and you get this. And then you have a function f of h, that's a wettability that captures your wettability. We can talk about this later. And then you need something like an external chemical potential that would be chemical potential in the gas phase. Now, this wetting energy is connected to something called the disjoining or the Yagin pressure that some people have maybe heard of, that you can actually measure. And it's the negative, so the derivative of f with respect to h is the negative of the. And taking the mobility, as I have written it there, h cubed, plugging the energy in here, then we come actually to a form of the equation. I hope you can see it like this here. And this is actually what you get if you take Navier-Stokes equations, boundary conditions at free surface and substrate, and do a long wave expansion, sort of 2 pages of calculations. You come to this, what is called the thin film equation, mesoscopic hydrodynamics, or how you want to call it. Right, so you have, again, now your flux is the mobility, that is h cubed over 3 eta, times the gradient of the pressure, and the pressure is Laplace pressure and discharging pressure, right? And then you have evaporation that comes for free. You get the Kelvin effect, dependence of evaporation on capillarity, and you get actually also the dependence on wettability. Right? Okay, so you notice I sneaked in the Q, right? Because the Q is the only thing we need actually from the derivation from the full hydrodynamic equations. It's the only thing that what we need the long wave expansion for, because we cannot postulate. I mean, we could postulate it, but people want to have reasons. Okay, so with this, you can also include gravity and describe actually droplets on an incline, but you can also make it more complicated by saying, okay, let's look at a thin film with a surfactant layer on top, or a thin film with a solute like nanoparticles, or polymer. And then you need to expand your system to two equations. And you see you have a film height, and here you have the amount of solute. I come to this in a second, what is meant by this. And then you have this matrix form where you have all these four parts, this different thermodynamic forces, and you have evaporation as well of the right? And the curious thing is, I mean, these equations we have also derived from the full hydrodynamic equations. And then what you find for this mobility matrix, you find the following structure. So you have the h cubed over 3 divided by eta from what we already know from the thin film equation. And then you have these other terms here that have a nice sort of internal structure. And you can actually describe both cases, let's say the solution or suspension film, or the film covered by insoluble surfactant, by choosing these values of these parameters A and B. And now let's talk a little bit about which fields I use as psi. The important thing is, in my opinion, to really set it up in a consistent way that, let's say, H and psi are similar type quantities. Let's say, in this case, they should be both effective heights, right? But they could also be effective densities. So if you mix it, then it gets more complicated. So what we use here, it's not the concentration that's vertically averaged in the film, what would be the first choice if people tried that. But you get into trouble with your variational calculus because these two quantities are not independent of each other, right? Because if you fix the particle number locally of the solute and you change the film height, then the mean concentration changes, right? So you cannot vary them independently. However, if you take H and you take psi, and psi is this H times this height average concentration, then this is like the local amount expressed as an effective film height. And then it's very easy to write everything down, right? And for the surfactant, it's more intricate because gamma is the concentration living on a deformed surface. So if the surface deforms, then the local gamma changes without changing the particle number. So you need to project it on the Cartesian plane. This projection factor, what is essentially the metrical factor, what makes things a bit complicated in the variation. Okay, now let's apply it. So this was sort of the introduction to how we want to do things. And now let's apply this to the adaptive substrates. And so the system I have in mind is became sort of fashionable in the past years. I mean, people understand dewetting on solid substrates quite well. They looked at topographically structured substrates. They looked at wetting patterns over the past 10 years or so. However, what they look at now is substrates that consist of different types of polymers with nanoparticle fillers, mixtures of different polymers that form a brush. And the interesting thing is there that if you put a droplet on top, then the substrate changes. Right? For instance, here, if you are, let's say, in some gas phase, then here the black part wants to be on top. However, if you immerse it in water, then the red part actually wants to. Or in this simple case, you have a dry brush in air or dry polymer layer, and then in the liquid it swells, and it can swell by a factor 10 or so, right? So it has a topographic effect, but also the wettability will change, the interface energy will change. And as these layers are also elastic, you get sort of poroelasticity and so on. So the moment you want to model this, let's say, as a good applied mathematician, you would start from really Navier-Stokes and then try to get constitutive laws for the layer and so on. And this will be extremely complicated. And so we tried to find a simpler way based on just this energy, this gradient dynamics formulation. And so our strategy was we very well know how to describe a droplet on a rigid substrate, and the droplet is non-volatile, right? And we can also look at volatile droplets, however, only if we impose a constant outside chemical potential. But that's actually not the case in experiments. In experiments, evaporation is often driven by its diffusion limited. So you need diffusion in the gas phase to, for instance, describe the coffee ring effect when a drop of coffee evaporates. Okay, so first we need to include phase change with full gas phase. We do this by putting second plate on top, and then we can also average the vapor concentration in the gas phase. And then we also go from the rigid substrate to the brush substrate, but still not volatile. And then we combine these two, and that's the model I want to show. And the strategy is very similar what you can also do for standard rigid porous substrate. Essentially, for a nice and simple model, you just need to change the energy from the brush energy to this one, and you get also a model that describes now already the first experiments. Okay, now this is work with Simon and recently also Daniel, and we look now at the droplet on a brush layer in a gas phase, and the fields we will use to describe this is the film height profile on top of the brush layer. And then the brush layer is actually a dry height, H dry, that is here, plus an effective height that comes from the swelling. You see these two are height. And then in the gas phase, we have actually a total density that is a constant, because in the gas phase, concentration, or let's say, pressure differences are equilibrated with the speed of sound. So that's much faster than what happens in the droplet. So that means the total density has to be constant. And so you have the vapor density plus the air density is this constant. And now if you divide this vapor density by a liquid density of the droplet and multiply it by the effective height here, then you also get to a local amount of that has the same dimension as our other two fields. And there are actually experiments by Ursel and Kapp at the University of Twente, in the group of Freda Mugele, where they looked at droplets of oil where they thought it's non-volatile, and they thought they have a closed experimental box. And then they found something. So this is a droplet. And you see here as interference pattern, you see the profile of the swelling brush underneath. Right? And what they found is that over many hours, a halo, a macroscopic halo developed, where the brush is higher with a halo profile. And the halo profile did, for instance, not change between hour 7 and hour 24 of the experiment. And they did not understand this. And what turned out is that actually first, their droplet was slightly volatile. And second, their box was not ideally closed. So it was a non-equilibrium situation. And I will show you how we model this. Now, you see, gradient dynamics is, from the concept, is nice, but the moment you write it down for three fields, now our fields H, theta, and psi, where H is the film height, theta is the effective height inside the brush, and psi is defined as I described before. They are all effective heights. So you get actually many terms, right? But now we need to discuss all these terms. But in the case that we study, it's actually very simple, because the three layers, the three regions are not dynamically coupled. There's no shear stress at the end, right? The gas phase is just diffusing. The liquid is just convective motion. In the brush, we assume it's just diffusing, right? So, and then this is a diagonal matrix. This is the mobility of the thin film. This is the diffusive mobility in the brush, diffusive mobility in the gas phase. However, now the M, what is the exchange? This is more complicated because you have to allow that liquid goes from the brush evaporating directly in the gas phase. It goes from the liquid in the gas phase. It goes from the liquid in the brush. Right? So everything is allowed, but the structure is sort of logical. Each row, each column has to add up to 0, right? Because overall the mass is conserved. Okay, now what I claim is that setting up the general model, you only need to discuss the energy and you get essentially everything, right? If you pick the right mobilities in absolute numbers. So what is the energy? You have capillarity that now depends on H and on theta, right? Because it changes the interfacial tension. Then you have wettability. It also depends on theta and H. Then you have a liquid bulk energy that you need to, let's say, allow for evaporation. Then you need to assign an energy to the bulk. Then you have the vapor energy. You have even an air energy. That's also, these two are just entropic. This is just a constant. And you have a brush energy. So the brush energy is written down here. It has, it's actually Alexander de Gennes wrote that down 50 years ago or so. So it has an elasticity term and an entropic term, right? Because it's also mixing the brush and the liquid. And I write it here in C, and C is a concentration that is defined like this. And now we have to discuss how we adapt the interface and wetting energies. So essentially, we just do linear interpolations between the different limiting cases, right? Also something to maybe discuss in detail. Okay, this is how we explained where our mobilities come from. And then we get from these mobilities, we get the transfer fluxes between the different layers. And then you can actually write down the kinetic equation in what I call the hydrodynamic form, where you clearly can identify the pressures and the concentration gradients and so on, right? So, and here we do the slight approximation. We assume that the vapor density is much smaller than the air density, and the air density is much smaller than the liquid density. So there are 2 or 3 terms that become important that look actually very uncommon, but they become important if, for instance, you go from the case of vapor in air to nearly pure vapor. Then certain terms diverge and you get to other models. Okay. Now, let me move this here and show you this 2 times. So what we do now, I show you now a simulation where we see a drop spreading on the polymer brush. And this is the open case. That means boundary conditions on the right is just a fixed external humidity of the lab. And you see, this is also, I have to point out, this is an adaptive time scale. So you see the very first seconds where the brush underneath the droplet was spreading. And now we are already by 17, 18 hours. So these are all real parameters that Simon put in. He was really dedicated to put real numbers in. I'm not that, yeah, for me, this is too tedious, but he was really, really good. And you have seen that this droplet is still slightly shrinking, but this profile here does not seem to change anymore. Let me go back and show it to you again. Now I have to move it again. So now we are in the early phase. So here you see all the transfer fluxes. So brush is spreading, there is swelling locally underneath the droplet. The droplet shrinks very slowly. The gas phase develops its profile. That only depends on X. And now this halo here develops, right? And you see the halo develops up to a certain point, up to now, 6 hours, 7 hours. And now it does not seem to change anymore. And that's what puzzled the experimentalists a lot. And we have shown essentially that what actually happens, gas phase, people would normally intuitively say the gas phase dominates the liquid transport to the boundary. But that's actually not the case, because if you calculate the effective height of a liquid layer of the molecules in the gas phase, it's actually less than what is transported through the brush. So what actually happens, the liquid is transported through the brush and evaporates from the brush into the air. And you see, this is the green line here that is brushed to vapor. And at the very beginning, this was actually negative, so it would actually go through the gas phase into the brush, and then it reverses. So the moment you think more about it, it's sort of it becomes sort of obvious what happens. But here, as a contrast, I showed you the same simulation, but now with the boundary closed, right? And there you see it. The profile has continuously developed, and it's still slowly going up, but it's a very slow process to equilibrate. But there's never this range of times where it does not change. And this is then stopping when the gas phase is saturated and the brush is flat. Okay, I have always to put this empty slide in because there's some bug in LaTeX with the movies. So, okay, this is summarizing what I have shown you in the videos. This experiment in theory, open chamber and closed chamber. And we see here really the swelling ratio, alpha is the swelling ratio of the brush. So in the open chamber, after 60 minutes in the experiment, nothing happens anymore for here up to 720 minutes. In the closed chamber, you see 60 to 147, 120 minutes, it continuously increases. And that's what the theory brings. So we did not extremely fine-tune the parameters. So here we need about up to 4 hours until it saturates, and then there's nearly no change anymore. Okay. I mean, this sort of convinced us that this idea of modeling is quite nice, but I mean, the process itself is not extremely exciting, right? So, however, there are other interesting experiments around. So I show you first the movie. So what people do, I mean, I as a theoretician don't really like that experiment because it's difficult to analyze in a systematic way. But what people do in the experiment, they take a syringe and inflate a droplet on a brush, and then they suck out the liquid again. Right? And then they do this even several times and see how it depends on history, what the droplet does. So that's what we do here in the simulation. So we start. With a droplet, it relaxes. Now we flood liquid in, and you see it does a stick slip motion. So this shows contact angle over contact line position. And so it moves in a stick slip motion. But it's not some sort of a very regular pattern because the droplet is inflating, right? So it's not it's not a time periodic state because of the geometry of the system. And then you recede again, so that's rather boring. And so this happens when the contact line advances. That means when the substrate essentially effectively moves into the droplet, right? So what we now did, okay, so this is a typical experiment where they see the same behavior. So this is by actually it's more than 10 years old. It's a Chinese group published actually in a Chinese journal. And I know there are several papers under considerations right now where people sort of revisit that system. So what we said, okay, let's do this a bit more systematic. So we take a meniscus, a liquid meniscus. We have our brush-covered substrate, and now we take the substrate and move it with a constant speed, essentially into the meniscus, right? And then this is really nice, and the straight contact line essentially, and you can then actually see a very nice and periodic stick-slip motion, and you can analyze the period independent of the speed of the substrate and so on. And so essentially what happens, the substrate moves, the contact line is pinned at this wetting ridge and then at some point the contact line gets too steep. So there is a Gibbs condition not fulfilled anymore, and it slips, right? So there's a stick slip motion. And interestingly, if you measure all the contact lines here, the contact angles here on the wetting ridge and the one of the liquid, there is a region where the brush, which one? The liquid gas interface angle has a negative slope independent of the velocity. In this region, you find essentially the stick slip regime, and even with some hysteresis, right? And one can analyze this in detail. And this is actually now online on software. Okay, so yeah, I have to accelerate a little bit. No, maybe not. Now, this was a typical example of what we have been doing the last 2 years on the adaptive substrates. So we also worked on simple models for droplets on elastic substrates, and now try to, let's say, make more complicated models, because many groups actually look at droplets of mixtures on funny substrates. And let's say, if you want to do this with a full macroscopic hydrodynamics, I think you get lost in parameters, essentially. So we believe that with this gradient dynamics approach, I mean, models get larger. So I'm at the moment developing one that has 7 fields. So it looks tedious if you write it out in full, but it has a very logical structure. You need to define your energy clearly, you need to get your mobilities, and then everything is set. And then everything is automatic. You have Marangoni effect you get osmotic fluxes, for instance, between, let's say, a biofilm and an agar substrate. It's all sort of automatic. And the warning is, I mean, I know several groups that try to do these models in a different way, and they inadvertently often break this gradient dynamic structure. And then you can get oscillatory states that aren't physical, for instance. Okay, now let's break the gradient dynamic structure intentionally. So how can we do this? So this was the structure that I had shown you at the beginning. And now, how can we break that? So normally I would actually have maybe votes how we can break that. And so something I wrote down is you could, for instance, add to the thermodynamic chemical potential or pressure, you can add another one that's non-thermodynamic. So that is a chemical potential, a non-equilibrium chemical potential that you cannot obtain as a variation of some energy function, right? And the same you could have in the non-conserved part. Yeah, I call it differently because it combines it with other terms. But also you could actually break the structure of the mobilities, right? You could make it non-positive definite, so you could make it indefinite, and you could break the symmetry, right? You could add an antisymmetric part. But this is a disclaimer, so I think this is neither complete nor unique how I have written it down, and this is actually something where some mathematician could look into how to. I mean, my linear algebra was too weak to actually come to a unique way of writing a broken view there. And now people do this in many models. So if I sorted them here, examples, I sort them here by how many fields they are conserved. So if no field is conserved, and I just do it for 2-field models, for instance, any 2-field reaction diffusion system that is normally studied is an example, right? Or the classical Turing systems. Biofilm models typically fall under this. Then also the complex Ginzburg-Landau equation would fall into there. So that means actually the Schrödinger equation is actually even in this. It is actually the opposite, right? The opposite of the gradient dynamics, because it only has an antisymmetric mobility tensor matrix. And 2 more closed models. If with 1 field conserved, what is very fashionable right now is to look at reaction diffusion systems with 1 conservation law, and actually digging into the literature, one finds this was developed here in Japan about 15 years ago, but is now a boom, for instance, in many groups in the West, in the context of modeling of protein reactions in cells and so on. Thin-film models for active liquids, I will show you a bit about this. Active phase-free crystal models. These are models where you look at crystallization, not of passive colloids, but of active colloids that move around. And by the way, the olive ones we have worked on at some point, and I can discuss this. Models for chemotaxis, tumor growth. And then if both fields are conserved, this should be actually in. No, so you have 2-layer liquid films with heating. So heating would be the breaking the gradient dynamics, but also the quite fashionable, right, non-reciprocal interactions of different particles in modeled by Carnot models or phase-free crystal. Okay, let's talk about thin film description for active liquids. But the situation I want now to consider are droplets of some active liquid on a solid substrate. Substrate is very simple, smooth and homogeneous. And the activity I describe by a polarization field that is also vertically averaged in the droplet. Right? And this is work with Penna, Sarah, and Karin. Karin is a CNRS researcher at Grenoble, and Penna and Sarah were PhD students that have both finished their work. So, and the idea is that these type of models are sort of very simple models of systems like keratocyte cells, keratocytes that are fish cells on solid substrates, and they can either be in a resting state or in a moving state. And actually, this happens at the same parameter values that people can control. So people normally say, oh, they are either pinned or they are not pinned, or there are some biochemical factor. But let's say modeling can be done either, or is done either with, let's say, rather simple phase field models where you say inside the cell is state 1, outside the cell is state -1, and then you write down a phase field model and you drive it with some polarization also. And you impose some global mass conservation. So this is typical models followed by Falco Sievert and Igor Aronson. Then if you come from the full hydrodynamics and you say, okay, let's take model H that couples Navier-Stokes and Carnot, convective Carnot equation. That's called model H, and you make it active by self-propulsion in a certain finite layer. The problem is you have then the free liquid-air interface, moving contact lines, so you have to do a lot of dirty tricks to be correct there. And these are very expensive 3D calculations. And this is done by, for instance, Cates, Marandusco, and so on. And then you can try to derive thin film equations. That means you have small slope systems, then you have these long wave models. There are several people that tried this with different methods. Let's say none of those had really a fully consistent and let's say transparent model that is a local model. I mean, there were, I think, closest came München Wagner, but they had actually integral differential equations that everywhere depended still in vertical profiles. And then actually here, again, Masao, and then with people now in Tishen Qian. I mean, I think he worked also with Masao at some point. He's in Hong Kong and Xiaopeng, I think. So he's somewhere in China, right? They wrote down sort of more effective models by focusing on quantities like the drop radius or the contact line slope, and then wrote down via Onsager's variation in principle directly ODE systems for this quantity. Okay, so we follow this thin film approach and say now we have this height averaged polarization. We have the film height, and liquid is non-volatile, and P can be changed by advection, so it can be advected by the liquid, but there's also translational and rotational diffusion. And most importantly, we have coupling terms with the slope of the free surface. And so we build this on our gradient dynamics approach, where we take actually the gradient dynamics for mixture, and we expand it from a concentration and an effective solute height to a polarization. But the polarization, so now these Q's are actually tensors that are more complicated, or matrices are more complicated. But the black structure is essentially a gradient dynamics, right? So the moment I write down the energy, everything else follows. Now the red parts is now activity. So you could see it as a type of non-equilibrium chemical potential, but be careful because they have a vectorial characteristic, right? Because P is a vector. So alpha is self-propulsion. That's in the model, but we do not consider it in what the results I showed you. And this is active stress, and active stress is just a tensor product of polarization with itself. And then we have a mobility matrix also modeled on what we have from the mixture. And so I insist that without the red terms, this is a thermodynamic consistent model, and then we add a bit of activity. Now the energy. We have capillarity, we have wettability, we have spontaneous polarization of the polarization field, right? So it wants to be polarized, and that gives us now the ability of defects, right? Because it wants to be either in 1D left or right polarized. Then we have an elastic energy of the polarization field. So this is a standard Frank energy in a simple approximation. And then we have this coupling between the polarization field and the free surface, right? And we can discuss the individual terms, but the one in red is the important one, because I say it depends really on the direction at the free surface in which direction is preferred. So there's always a preferred direction depending on the sign of this parameter CHPA. And so let me jump directly into the 2D results that are just obtained by time simulations, right? So we start with a droplet, a relaxed droplet without activity, and then we switch on the activity and we map what happens after rather long simulations, and we have different states. So if there is zero active stress, then we have either a resting droplet with an aster situated on the boundary. So an aster is like this hedgehog-like structure, or we have actually a central aster, but it's resting, and this depends on the strength of this surface polarization coupling, right? So this would be the central aster. However, if we go away from zero active stress, then we can actually have a moving droplet, and it's normally a moving droplet must have a boundary aster, because if you have a symmetric situation, then it will not move. And then actually we have this large yellow part where you find things like that. Droplets are splitting, right? And all this is for the same droplet volume, and it will depend on droplet volume. We have not the computational ability to actually do a 3D phase diagram. And now the interesting thing is, if you fix the active stress, I think at this value, what is the dashed line, and you change the surface polarization coupling, then you see a hysteresis between a resting state. So this is velocity here, a resting state and a moving state, right? And we believe that such type of a hysteresis could be responsible for this hysteresis in the experiments I described to you. So let's look a little bit more at the mechanism. So now I show you some of my favorite bifurcation diagrams. So normally I like to analyze bifurcations for all the systems. But in many of systems, we came now to stages where bifurcation diagrams are too complicated to actually show in a talk, because you can't even explain them, because they are very involved. You will see these are sort of semi-involved. They are sort of fine. So if we take passive drops, no polarization surface coupling, then that's just the bifurcation diagram you would also find very similar to something you find in the Andrea's equation. So you have the homogeneous state. So this is parameter in the surface. No, this is in the spontaneous polarization term, and this is some solution measure, a norm here. Right. So you have the droplet that doesn't really change too much of the shape, and then you have all these branches that branch out of the homogeneous state, and this one is the only stable one, and the other ones are unstable with different number of eigenvalues, and you see no defect, one defect, two defects, three defects, right? That's where the polarization was zero, right? So that's the basic, and it will turn out that actually these two states are still very important also in the activities. Now let's switch on the PS coupling, right? And then things become interesting. Now we take on the x-axis the strength of this coupling. So this is actually the state we have seen before. These two states, this would be, say this one is the state with, you see, this is no, this one. The red one is a state with a central defect, and the blue one is actually a state we have not yet seen in the diagram with a defect on the boundary. And you see, if I increase this coupling, then the state with the defect on the boundary will actually vanish in the second node bifurcation. And there is a pitchfork bifurcation here where the state with the central defect gains stability. Right? And if you look at the energies, because this is equilibrium, you see the energies have a crossover in the middle of the hysteresis region where both of them are linearly stable. So in principle, they can, at this point, this is a Maxwell point, they could coexist even. Right? Okay, so this bifurcation structure of the existence of these two solutions, one symmetric, the other one asymmetric, actually is the central mechanism, central needed thing to have moving and resting droplets if you switch now on the active stress. Right? So here in the weak colors, I show you the diagram we had before. Now I fix an active stress, and you see what changes are two things. I mean, everything shifts a little bit, and then actually this one here was subcritical, so it bifurcates towards the stable state. However, here it's actually supercritical and has another saddle node bifurcation here before coming to this saddle node bifurcation we knew from before. So actually there are two stable states, linearly stable states, and they are distinguished. So these are now moving. These are moving states, and they are distinguished in their speeds. What is sort of interesting, let me see whether I have the speeds. Yeah, here I think I have the speeds. So imagine you come from here, you change active stress from 0, you crank it up, and then at this point your symmetric state loses stability. And then you jump on this, you go on this branch with a low velocity, that then you come to this point where this branch ends in a certain node bifurcation, and then you would actually jump up to a larger velocity. So this is like I mean, if you call it a cell, it would be a cell with 2 gears. I'm not sure whether this exists, but we found this very, very interesting. Okay, then you can do sort of crazy stuff. You can now sort of have different contribution in this surface polarization coupling, where you have sort of 2 parameters that sort of describe the coupling that is orthogonal to the surface slope or parallel to the surface slope. You can penalize one or the other, and then what you actually find, you find also this vortex-like states. So you actually introduce chirality via the boundary conditions. And then what you can actually find transitions from left-right symmetric drops that move, in this case, in this direction. And then at some point, they would decide that now they want to break this left-right symmetry and actually then move in circles. So however, you see, I mean, these simulations are quite expensive computationally. So we do not yet have a systematic picture of this, and also Hannah finished her PhD. So we will see whether we can continue this example. Okay, so I'm actually quite good in time. I should stop this. It makes noise. Because that's essentially what I wanted to show you. So I wanted to go through, let's say, the basic idea of what is a gradient dynamics, then have this for many different scalar fields, and then make a simple example that is already quite a bit more complex than what one is, let's say, used to see in the literature for this droplet system, right? So this was the droplet that's volatile on the brush. I think I tried to convince you that first it's sort of easy to set up, and then it shows already interesting results, right? For this experiment from Bente and the stick slip motion, it's actually, I think, the first detailed investigation for stick slip motion of on elastic or brush-like substrate. For the elastic substrate, it's also observed. There are quite a number of experimental papers. from the group of Lima, for instance, in Paris, Laurent Lima. And there is one theory paper with a full non-linear elasticity, hydrodynamics coupled time simulations that in their simulations can actually show we also see stick slip motion, right? But with these simulations with very high effort, you have no chance to map out how does the period depend on speed and things like that. So there you need more simple models. And then I went from the passive case and let's say try to give you a systematic picture what one could do now to this type of gradient dynamics models to make them active, right? And if you then go through the literature, I mean, there is not too much systematics about all this, the models that I have listed there. So this would be my dream for the future, probably after retirement. Sit down, look at all these models and try to put them in a general framework and find relations between models that people have not seen up to now. Yeah, and then I took these active droplets and set up this relatively simple model. And I emphasize this is not derived from the full hydrodynamic, let's say, active nematic or active polar liquid crystal models, right? This is postulated. Right? So if you want to derive it, I would say it's if it's in the region, in the parameter region of very weak coupling, weak anchoring at the free surface and the substrate, because we assume that the polarization field does not change much across the film. Right? So then we introduce this surface polarization coupling that sort of couples this direction of the polarization with this local slope of the free surface. And this then allowed us to see this hysteresis between resting and moving states. Right? And if you want now finally to look at an outlook, so I think I will give more talks in Kyoto. And I think there will be one where the non-reciprocal Canhert model will be quite prominent in. So essentially this is like you take a Canhert equation for this phase separation and if you go to a ternary mixture, you couple two of those, right? And then people introduce let's say a predator-prey interaction essentially between two components. So component A likes component B, but component B hates component A, right? So that breaks Newton's third law, right? And makes all this system totally active, right? And then you can have the transition, you can arrest and suppress the coarsening that you always have in standard Canhert models. You can have the emergence of motion and of oscillations. And there's also some more mathematics behind, because we think this equation is actually much more important than people think in the general systematics of, let's say, of nonlinear equation. Yeah, and then for the adaptive substrates, I mean, we also put this on porous layers, and we have, as I said, a detailed analysis of stick slip motion and the bifurcations there. And I think Aki and you are interested in the phase-free crystal modeling and the active phase-free crystal, so we will have a talk about this probably late in July, I guess, in early July. And okay, biofilm modeling is also something where historically people often start from a reaction diffusion model, and then when they notice they get nice fingering structures or so for this growing biofilms, but they can't get certain aspects without introducing some hydrodynamics. So then they put hydrodynamics on top of the RD system. And so we decided to do it the other way around. So we started from a thermodynamic consistent mixture model that includes wettability and all this, and then introduce sort of the bioactive terms of growth and of biosurfactants, and then could, for instance, analyze an effect where osmotically spreading biofilms seem to, the spreading gets arrested if sort of the wettability is wrong, let's say, for the biofilm, right? And you could see nice transitions. Okay, with this I end. I put up for the video, I put up the references for a second so people can in the video see all the references. No, I will not put the supplementary material. Okay, thank you very much.